All right, everybody, welcome to Chapter 3. This is where we're going to live the rest of the trimester. It is. Chapter 3 has 9 sections in it. It's massive. Basically, the entire chapter is focused on just calculating derivatives. So the beginning of the chapter, we're going to talk about, like today.
Can I go grab my notebook real quick?
Real quick, yeah. So today we're going to talk about what is a derivative, and so how it's related to some calculations you guys have done before. Then we're going to move into differentiability, which is how do you know if a function has a derivative or not. And then we're going to talk about the whole rest of the chapter, basically techniques of taking a derivative for whatever kind of function you might have. So there's a whole section on derivatives of trig functions. There's a whole section on derivatives of logs and exponentials. There's a whole section on doing derivatives of rational functions. So we kind of break it up into all these little chunks, but there are lots of different functions out there, and each one of them we're going to hit and talk about until at the end of this chapter, I can give you any function in the world, and you can take the derivative of it and explain what that means and use it. So there's a lot to do, so it's kind of long. All right, but today we're just going to kind of like lay the groundwork as far as, like I said, what is a derivative. So 3.1 is just simply called derivative of a function. Okay, so the definition of a derivative is going to look kind of familiar because you've actually done it before. The notation that we use for a derivative looks like that. Actually, there's more than one, but this is the first one we'll look at. This is the Newtonian way of writing it. Okay, so Newton studied calculus, and many people believe that he invented calculus or discovered calculus or whatever. So when he was talking about derivatives, he used this little notation. It's f prime of x was his derivative, and here's how he defined it. It is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. What is that? Instantaneous rate of change. Guess what? That's a derivative. It's just another name for a derivative. You've already done it before.
We better stop now.
I know, it's crazy time, right? So derivative is the instantaneous rate of change. Okay, and we're going to look at two different ways of viewing a derivative, I guess. There's a derivative at a point, which is what you guys have done before, and then there's a derivative function. Okay? This right here is actually a derivative function. Now I'm going to change this just slightly to make it a derivative at a point. What's the only difference between those two things? Yeah, instead of x, it's a, right? And so x is a variable. It stays a variable once you're done. A is some number that I'm plugging into it, okay? So this is going to be the derivative at a point x equals a. So it's really doing, the calculation really is the same thing. It's just instead of having an x in there, you're immediately plugging in a number for x and doing it that way instead, okay? And we've pretty much been doing this kind of thing. Derivative at a point. But let's see if we can do the derivative function too, though. Okay? So let's say f of x is equal to 2x squared minus 5, and the directions will be something like find f prime of x. So we're going to go to our derivative function. Notice how it doesn't say f prime of some number, it's f prime of x. So we're doing this one up here, the derivative function. Alright, so f prime of x equals the limit as h goes to 0, f of x plus h. So 2x plus h squared minus 5. Okay, so that's the f of x plus h. And then minus f of x. Okay, well, this is f of x, right? So it's just that whole function, 2x squared minus 5, getting subtracted. And then all of that divided by h. And at this point, it's kind of the same game we were playing before. You got to multiply everything out, distribute everything, get all of that numerator as a bunch of terms all added and subtracted up at the top, and then see what cancels out. And we're hoping, again, that that h should cancel with everything on the top so that you have something then that's usable where you can actually come up with the answer. So let's go through that then. So we got limit as h goes to 0. So let's see, if I multiply that all out, so I'm going to have 2, and then that's going to be x squared plus 2xh plus h squared minus 5, and then I'm going to distribute that negative, so minus 2x squared plus 5, all divided by h. And then I got to distribute that too real quick, so let's do that real fast and check to see what we got there then. So 2x squared plus 4xh plus 2h squared. I guess we could just get rid of the minus 5 and the plus 5 at this point, because those will cancel each other out. Okay, anything else in there you guys see that it's going to cancel out? The 2x squareds will be gone. And then once I divide everything by h, let's see what I got. So this h will be gone, and then the square on that h will be gone. So it'll be the limit as h goes to 0 of 4x plus 2h. Everybody follow me there? Did a couple things at once there. And then what is my answer? Because I can plug the 0 in now for h. 4x. Congratulations, you have calculated your first derivative. That is a function. So f prime of x equals 4x. All right, there is a lot of power in what you just did here, because what you have now is a derivative function, which means if I want to find the instantaneous rate of change of this original function, 2x squared minus 5, let's say at 2, what's the answer? 8. If I want to find the instantaneous rate of change of that original function at 4, what's the answer? 16. At 0, 0. So anywhere on that curve I want an instantaneous rate of change. If I'm looking at the tangent line, the slope of the tangent line, anywhere on that particular curve, I can find it now. I don't have to recreate this whole limit as h goes to 0 business for every single one of them. I have a function I can use. I can just plug right into that thing and get my answer every time. Okay? So this chapter, I said we're going to be focusing on calculating derivatives for whatever. We're going to be coming up with these guys. We're going to be coming up with derivative functions that allows us to plug whatever we want into them for that particular function and not have to keep doing this limit thing over and over and over and over again. Okay, so that's how I'm doing that. Okay, so let's try this one more time, just so we're getting used to it. Let's do f of x and we'll do one that we haven't really approached before, but we can probably access here still. F of x equals the square root of x. And let's find f prime of x for this one. Okay, so that definition then tells us f prime of x is going to be the limit as h goes to 0 of f of x plus h, so the square root of x plus h minus f of x all over h. Okay, so when we try and do this now, remember what we're trying to do is we're trying to figure out how we could simplify that numerator so that we can get things to cancel out. Okay, so what do you notice about that? Guys have any techniques of ways that we could simplify that numerator? Give you a hint. It's okay to say no. No, I don't know. No. Square root of x plus h minus square root of x? No, not particularly. So there's an alternate definition of a derivative that we can use, and we're gonna for this one, okay, that might make it a little bit easier. And this is a derivative at a point, so it's f prime of a, but it'll help us with this as well. Whoops. Whoa, sorry about that. Oh, thanks. Okay, so it should look somewhat familiar, like at least it looks similar to the one that we looked at before, but a little bit different. Okay, so instead of using h, we're just using x. So it's the limit as x goes to a. It's still on the top, kind of a change in the y, on the bottom, change in the x, except we're doing the limit as x goes to a. So think about that. If I tried to do this as a substitution limit again to start off with, what would I end up with underneath here? If I substituted a for x right away, it'd be 0 on the bottom again, right? So again, we are looking for some way to simplify this thing as much as we can to kind of eliminate this x minus a. And when it comes to functions like this one, it's going to be a little bit more useful because we don't have that h floating around in there. Can I help you?
This is Mrs. Camp.
Okay. Okay, so let's see if we can apply this one instead. And remember, we're looking for f prime of x, but what we can do when we're done, if we apply this definition here, is we can just change the a into an x at the end, because that's really what we want, and just use it that way instead. So back this back up so we can see both here. All right, so instead, let's go this route. So we'll do, like I said, f prime of a and then f of x is the square root of x. F of a would be the square root of a over x minus a. Now, some of you guys might look at that and go, okay, Mr. Herrick, that's not much better than the last one. There's still really nothing that we can do there. But in this case, there is, and we have to get a little bit tricksy here with it, but we can do it. So first of all, does everyone see how I'm essentially multiplying this whole thing by 1? Right? And by multiplying by 1, I'm not changing the value of it, so it's okay to do. Right? Okay. Now, the question becomes, how in the world did I come up with this, though? Square root of x plus square root of a, square root of x plus square root of a. It's all based on this over here. Okay? We have it square root of x minus square root of a, and over here now is square root of x plus square root of a. If you multiply these two things together, and they are conjugates, one's a minus, one's a plus, other than that they're the same. When you multiply conjugates together, things cancel out kind of nicely for you. So take a look at what happens next here. So we have the limit as x goes to a. On the top, square root of x times the square root of x would be just x. And then you're going to have negative square root of a times square root of x, so minus square root of ax, and then you're going to have square root of x times square root of a, so plus square root of ax, and then square root of a times square root of a minus just a. And then on the bottom, x minus a square root x plus square root a. I'm not going to multiply those together just yet, and I'll show you why here in the next step. Okay, but everybody with me so far? Just distributing the top, not distributing the bottom yet. And canceling stuff out up there, I'm just going to have x minus a left over. And then on the bottom, x minus a square root x plus square root of a. What do you now notice? You've got a factor that cancels, and in fact, it's that x minus a factor, which is the one we kind of sort of wanted to get rid of, right? So that we can actually try substituting that a in there. So with both of those gone, got the limit as x goes to a of 1 over square root x plus square root a. And so if I take this a and plug it in now, because I can, I have 1 over 2 square root a, because it would be square root a plus square root a underneath there then. Okay, so if this is f prime of a, right, work through all of that to get there, then what is f prime of x? It's not supposed to be a trick question. If f prime of a is this, what's f prime of x? Same thing, but the a is now a x, right? Yeah. So f prime of x equals 1 over 2 square root x. Got it. Okay? And we were able to go through that alternate definition to get there. Okay, using this a as kind of our little placeholder for x. So this right here, this definition, this is an important alternate one. Sometimes when you're calculating a derivative, trying to use with the as h goes to 0 way, you run into a roadblock, and then maybe you pull this one out instead and try it, and yeah, see how it goes.
How did you get 1 over 2 square root a?
Because if I plug an a in for x down there, because I can, it's not going to make me divide by 0 now. I'd have the square root of a plus the square root of a, which is 2 square root a. So, doing like the calculation stuff of derivatives, you guys are going to have some practice with that in your homework, and that's all well and good. The other thing that I'd like to talk about with you guys is this relationship graphically between a function and its derivative. So we're going to look at how do you graph f prime from f. And this is going to be kind of an inexact science. It's going to be a little bit of guesstimating and stuff like that to kind of get an idea of what the shape would be. So, there are going to be some answers that might, like, one person sitting next to another person might not have a graph that looks like exactly the same, but we're looking for some key features from one or the other. So, all right. So let's start with a graph here of f. All right, and we'll put some scale on this thing here. We're going to point out some key points here. So this particular point is going to be at 6. This one up here is going to be at 2. And then at 3, be right there. And this one, I'm just going to tell you, the slope is equal to -1 at that spot. And then at 5, same thing, they'll have the slope equals -1. And then at 1, that'll be the slope is equal to +1. Okay? Okay. And the y value, because an instantaneous rate of change is measuring what about a function? Its slope, right? So if we're trying to figure out f prime from a graph of f, do I care one bit about what the y values are? No. All I care about is what's the slope, what's the slope, what's the slope, what's the slope, bless you, from each one of those points as we go through it, okay? So just keep that in mind. I'm checking out slopes as I go, and then I'm going to use that to make f prime, okay? So I'm going to come over here and make a little chart. You don't have to do this every time, but I think this might be helpful as we kind of look at this originally. Actually, you know what? I don't even need that last column because I don't care what f is. I just want f prime. Okay, so for each one of these, I've got some x values that are some points at some specific x values of interest here. So we did when x was equal to 1, 2, 3, 5, and 6. Okay? F prime is the derivative. The derivative is the instantaneous rate of change. The instantaneous rate of change is the slope. The derivative is the slope. Okay? You're measuring slope. So f prime, I'm just recording slopes for all those points. Okay? So this one we said we had a slope of 1. So f prime at 1 is 1. At 2, think about tangent lines again. Here's at 2. The slope of that line is 0, right? So 0. At 3, what's f prime? -1. At 5, what's f prime? -1. And at 6, what is f prime? 0. Okay, so we've got, think about, slopes of little tangent lines at each one of those places. Okay, now in this particular picture, I gave you some slopes here of these points. In practice, you're not always going to have that to work with, so you might have to just kind of eyeball it and say, okay, then I guess it kind of looks like it might be 1 or 2 or something like that. Slopes are really hard to judge. I mean, as soon as you get a slope bigger than 1, I mean, how do you tell the difference between a slope of 2 versus a slope of 3 just by eyeballing it? It's kind of difficult. So that's why I said you might have some things where it doesn't exactly kind of work out. But important things to note, which we'll do in the next one, is where are the slopes positive, where are the slopes negative, and where are the slopes 0. Those are going to be your key places you're going to be interested in. And we'll dig in a little bit more on that in just a second. But in any event, since we have this stuff here, we can start making a graph of f prime now. And I'm going to need positives and negatives, so I'm going to draw it like that. And let's say 1 is up here, negative 1 is down there. Just to give ourselves a little bit of space here. All right, so when x is 1, f prime is 1. When x is 2, f prime is 0. When x is 3, f prime is negative 1. And then at 5, also negative 1. And then at 6, it's 0. All right, so do you guys kind of see the shape of this thing starting to come around here? What's it going to be in the shape of, do you suppose? Based on how those dots are on there. What kind of graph would fit that real nice? Parabola. Okay, so a sine wave maybe, yeah, okay. But no, it's a parabola though. So it kind of does one of these. Okay. So, and we'll talk more about this in the future, but if we're talking just strictly polynomials here, what kind of polynomial does it look like we had at the beginning with f? What degree does that look like it is? Cubic, right? Third degree? Looks like a cubic. What do you notice about this one? What happened to that degree? Drop down 1, right? Now it's a degree 2. It's quadratic. Okay? That is not a coincidence. That happens when you do derivatives. So, all right. So here's f of x. Here is f prime of x. The graph of that derivative function that we started with up there. Yeah. The degree of a polynomial is like x to the third is a third degree. X squared is a degree of 2. So, okay. Now, like I said, there's a key connection between these as far as when the slopes are positive, negative, and 0. Okay? So, in this original function, give me one interval where the slopes are all positive. From 0 to 2. What do you notice about the derivative from 0 to 2? Is it? The derivative from 0 to 2? It's not negative. Oh, okay. Okay. What happens at 2 to this function? From 0 to 2, it's all what? Positive, right? Look up here. Where from 2 to 6, it's all negative slopes, right? Look at 2 to 6 down here. What's true of the derivative? It's all negative, right? Because the slopes are negative. So the values of the derivative are negative. And then it turns around and starts to go up again, right? Slopes are all positive as we go here. So the derivative is positive there. After 6, it's all above the x-axis. Okay? Another way to look at it, wherever the function increases, the derivative is positive. Wherever the function decreases, the derivative is negative. Wherever you have, what are these guys called? Maximums and minimums, extrema, right? What's true of the derivative at those points? 0. Okay? That's the key stuff we want to look at. All right? So the next one, I'm going to draw a rough sketch of a function. I'm going to see if you can sketch me the derivative. Just thinking about that. Where is it positive? Where is it negative? Just the slopes, right? Where are the slopes positive, negative, or 0? And see if you can do it. All right. All right, that's all I'm going to give you. Here's f of x. We'll call it g of x. So here's your g of x. I would like you to sketch for me g prime of x as best you can. Matter. Because remember, we're only focusing on slope, right? Now, I could, I suppose. And your textbook probably will, too, to try and throw you off. So, sure, I'll put a scale on there. But, yeah, you really don't need it. All right, so let's... Or do you guys need more time?
No.
She doesn't. Anybody else? Looks like other people are finishing up still, so I'll let them finish. That's a good point. They chose not to answer. All right. Now, where I always start with these is the zero slopes. I don't know if you guys took that same approach or not, but identifying where are those horizontal tangents in the original graph. And in this case, I pinpointed them for you at 2, 5, and 8. So in your derivative graph here, you should have zeros at 2, 5, and 8 for your derivative. And then the question becomes, okay, so in between these then, is it above or below? How is it intersecting those? So in this first interval, what do we know about the derivative? It's negative, right? So we should be negative somehow. Now, I don't know exactly how negative. Like, it looks like it's about a slope of -1, about halfway there. So maybe it's, right here or something, or I don't know. So in any event, it's going down, though. So we start down there. Now, between 2 and 5, what do we know about the derivative? It's positive, okay? Now, here's the thing. At 2, it's 0, positive, 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 back to 0. So it's going to have to come up and then come back down, right? And think about that. In between, about halfway between 2 and 5, isn't that where it seems like it's the steepest? If you look at the original graph, do you see that? Right about in here, if I were drawing little tangent lines all along this thing, wouldn't the most steep one be about right here in the middle? And as we're closer to 0, to see how those slopes start to get shallower and shallower and shallower, and it's almost 0 until when you get right to here, it actually is 0. Same thing the other way. As we get closer and closer to 5, it's still positive slope, positive slope, positive slope, but it's leveling off until we get to 5. So those slopes are like really steep here and then shallower, less, 0. Okay? So that kind of makes sense that it does one of these then, because you've got very small slopes getting a little bigger and then back down to 0. So some kind of a little hill here, kind of like that maybe. And then from 5 to 8, what's true of that interval? Should be negative. And again, goes from 0 back to 0 again. So this is going to kind of swing around like that. And then the end, it is all positive. And not only that, it's all positive and they're getting steeper, 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 steeper as you go. So the derivative should be getting larger, 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 larger as you go out. So this is going to continue off, heading up. So something to that effect. Okay. Now again, like I said, this goes up exactly. I don't know how far this piece right here goes exactly. It doesn't matter as long as we have this correct shape to it. That's what I'm going to be focusing on when we're looking at sketching graphs of derivatives. Okay, so can we go the other way? Can I give you a graph of a derivative and you work backwards and tell me what the original graph looked like? Let's see if we can do that. So here's a graph of f prime of x. And I'm going to make it a little more interesting this time. You guys are probably like, when he says interesting, he usually means hard. 5, 6, let's say 9. Alright. And then this is, let's say that's at -2. This is 2. Okay, and then this would continue going that way. Okay, so I have a derivative. Let's look at this first little piece here. I have a derivative that is -2 from -infinity all the way up to 3. Okay? So my slope doesn't change. Remember, the values of this thing, everything on the y scale here is the value of the measure of the slope of the original function. We're using slope to go back to what the original one should look like. So I have something that has a constant slope of -2 until I get to 3. What sorts of graphs, what sorts of functions have constant slopes? Lines. Exactly, right? A line, we have slope-intercept form because that line's slope doesn't change. You can put it right in the equation if you write it a certain way. So from -infinity up to 3, I should have a graph of a line that has a slope of -2. So I'm going to jump down here and do that. Yeah.
Why is the slope -2 for the line? Isn't the slope of the line 0?
You're trying to go the other way again. This is the derivative. This is not the original function, right? So every y value on this thing is a slope. So we're working back to the slope of the line. So yes, we got a slope of -2. So up to 3, I need a slope of -2. So here's a question though. How do I know how high up or how far down that line is, right? Because all I know about that line is it has a slope of -2. So shoot, I could have a slope of -2 like up here somewhere or down there somewhere, and it's still fitting it, right? And the answer is it doesn't matter because there are several functions that could have this same derivative. Okay, and we're going to get into that a lot more later. But for now, just know I just need to make it a line that has a slope of -2. So let's see, if I have, let's put this up at, say that's 3, this is -3. So if I want a slope of -2, go down 2 and over 1, so maybe it looks something like this. Okay, if you calculate that slope, rise over run, down 6 over 3, that's -2, so that works. Okay, so we've kind of matched that part up there. Okay, then from 3 to 5, what do I know about the derivative? It's positive slopes, right? Remember, this is measuring slopes. So from 3 to 5, this is positive, which means this particular function needs to be increasing. The slopes are positive, right? So it's going up. Okay, then at 5, what happens? It hits a maximum, right? And it has to be a maximum, not a minimum, right? Because this is positive slope. So we're increasing, and then at 5, hit a maximum, and then from 5 to 9, it's negative, which means it's going to decrease, right? Then at 9, it hits another 0, so it's going to be a minimum, and then it's positive again, and it's going to come back up. Okay? So I know that's kind of hard to think about sometimes. You have to think it backwards a little bit. But even though this is decreasing right here, the fact that it's above the x-axis means this is going to increase. So I'm going to take this thing and have it start to increase until I get to 5. So maybe it does something kind of like this. And it doesn't have to go over that x-axis. All I know is it's increasing. Then at 5, I'm hitting a maximum. And then it's going to decrease until I get to 9, where it's going to hit a minimum. I should make this axis a little straighter. All right, so at 9, it's going to hit a minimum, and then it's going to take off from there. So it's going to come back down, hit a minimum at 9, and then increase from there. So maybe something sort of like that. Okay, not going to have you doing tons of these right away. Okay, this is a skill we're going to continue to develop as we go. And like I said, there are more than one right answer for this because all we have to make sure that's matching are the slopes. So, like, for example, this part where we know the derivative is positive, so it has to increase, it could have done this. It could have gone way up here. That decreasing could have just come down a little bit, or it could have come way down. I don't know exactly. So, I kind of do the best I can to piece it together backwards, but yeah, we'll do more of those later. Yeah.
How you have this continuity in there?
Mm-hmm.
If you had one where one side was open, one side was solid, would you just do like a jump function?
It might be, it might not. That's something we'll look into more later too. Okay. So, all the graphing stuff, the only thing that I want to talk about before we're done are these things called one-sided derivatives. And believe it or not, you guys actually have done this a little bit too. So let's say I have a function that looks something like this. To know what's the derivative at 0. So if this is f of x, I want to know what is f prime of 0. Okay, not f of 0, f prime of 0. So what is the slope there? If I asked you for the slope anywhere else on this thing, you could do it. But why can't I answer this question at that point? So the slope of it, like at that point, like instantaneously changes, right? As I'm coming at it this way, what does it appear the slope needs to be? 0. But as soon as I get there, this line now. And the slope of this line is certainly not 0, right? The slope of this line looks to be, I don't know, like 1 or 2 or something like that. Okay? So at this point, it has no derivative. What it does have is a left-handed derivative and a right-handed derivative. There's one-sided derivatives. Okay? So what is the left-hand derivative at this point? 0, because right, it's coming down and then the slope is approaching 0. What is the right-handed derivative over here? Like 1 or 2 or whatever the slope of that line is, right? So okay, if the left-hand derivative and the right-hand derivative are not the same thing, then we say the derivative does not exist at that point. And so in this case, there would be no just regular derivative at that point. And this is something we're going to get into big time in the next section. When we talk about differentiability, remember I talked about determining if a function has a derivative or can we calculate a derivative or not at specific points. We're going to be investigating this quite a bit. These left and right-handed derivatives. Are they the same or not? So can we actually find a derivative there? And what we're going to find as part of that, notice how this function is not like smooth through this point. It makes kind of a little corner, okay, because the slope is doing one thing and then all of a sudden, boom, it's doing something else. Okay, having a corner on a derivative makes it non-differentiable at that point. Can't do the derivative there. So that's kind of the idea. So let's try this once. I'm going to come up over here where I've got some more room. And we'll calculate some one-sided derivatives. Okay. There we go. Okay. So let's say we've got f of x. It's defined in two pieces. Go with the same thing that we had here. So let's say it's x squared when x is less than or equal to 0, and it is x when x is greater than 0. So what we're going to do is, and we already said we kind of know what the answer is, right? The left-handed derivative is 0, the right-handed derivative is 1. Well, let's go prove it. We're going to do this whole limit as h goes to 0. We're going to actually calculate it and show that they come out different. So to do the left-handed derivative, we're going to do the limit as h goes to 0 from the right, though. I'm sorry, from the left, so that'd be a little minus, not a plus. Okay. So remember when we did the left and right-handed limits, we had to put the little plus or the little minus or whatever. Well, the derivative then follows that same idea. So it's the limit as h goes to 0 left of f of a plus h minus f of a all divided by h. Okay. Now this limit coming from the left-hand side simply indicates then which piece I need to go with. So from the left, which piece am I using? First one or second one? First one, right? This is when x is less than or equal to 0. That's everything to the left of 0, right? So I'm going to use that piece in this limit then to do the left-sided derivative. So that's going to be the limit as h approaches 0 from the left. F of a plus h squared minus f of a would be a squared divided by h. But what is a in this instance? 0. So we got the limit as h approaches 0 from the left of h squared minus 0 over h. So that's going to be h squared over h, which is just the limit as h goes to 0 of h, which is what? 0, right? Plug it in. So the left-handed derivative is 0, just like we said it was, right? Rachel, question?
How do you know what A is?
Because we're determining if f prime of 0 is, or what the left and the right-hand derivatives are at 0, at this spot right here. If I had done it like over here somewhere, maybe at 2, then I'd be using a 2 for a, but we're doing it at 0. Correct. Yeah, and that's important to note maybe. A is the x value. So this would be like prime of a is what we're doing here. In this case, then we're looking at f prime of 0. So a is 0 in this case. Yep. Okay, so that's the left. Doing the right, same process, except we're using the other piece. The other side is 0, so it would be the limit as h approaches 0 from the right, so a little plus, of f of h minus f of a, all divided by h. And so in this case, I'm going to use just the function x. So it's the limit as h approaches 0 from the plus side. A plus h, so that would be just a plus h, minus f of a would be just a, divided by h. 0 again, so we end up with the limit as h approaches 0 from the right. And let's see, what do we got here? This is just going to be h over h, right? Which is the limit as h approaches 0 of just, well, 1, right? There's no h to plug into, so what's the answer? 1. Yeah, it just stays 1. Okay? So if I'm like giving you a problem, something like, okay, take this function up here, prove to me that the derivative does not exist at 0. This is what you would do. Okay, I'm going to show you that the left-handed derivative and the right-handed derivative come out to different values, so therefore that derivative can't exist at that point. And that's exactly what we just did. Okay, from the left we're getting 0, from the right we're getting 1. Derivative at 0 can't exist then. Okay? So it's doing all this limit business again. You just have to go one piece at a time and show that they come out to something different. The question might also ask you, show that the derivative does exist. So maybe even though it's in two pieces, maybe the slopes still end up coming out the same. So maybe it does connect nice and smooth and the derivative does exist there. So then you'd have to kind of go through the same thing, but then show that the two numbers are the same. Okay, so the idea with that. So just because you're going to see some of it, we'll get a lot more into this later, but I want to talk a little bit of notation stuff, and then I really will be done, I promise. I know we've done a lot today. There's a little history here that I have to let you guys know about. There are two mathematicians that were alive roughly the same time. Both claim to have, quote-unquote, invented calculus, but they were working completely independent of each other, and they had different ways of writing notations. And depending on what you do, how you're using a derivative, one notation is more accepted than the other. So Isaac Newton is the one, which we've already talked about. And then there's this French guy, Leibniz, who was also working on derivatives. And so we have Newton notation and we have Leibniz notation. But it all means the same thing, okay? So I just want to show you a whole bunch of symbols that all mean derivative, okay? So this is some Newton stuff. So f prime of x, you've already seen, that means derivative. You also might see it written just as f prime, without the of x. But it still means derivative. It's the same thing. Okay? Now, Leibniz, I kind of like his notation because it kind of shows you more of what exactly you're doing. His notation is dy over dx. And think about when we did all this instantaneous rate of change business, what were we really doing? Change in y over change in x, right? Now, dy and dx are these things called differentials, which we will also get into later. But in any event, do you see how that kind of shows a rate of change? It's a fraction, it's a ratio, which is really what you're doing when you're doing this kind of stuff. So he does it that way. Another way that he does his notation, depending on what you're doing, you might see it just simply written as d dx. Okay, so dy dx or d dx. Another way that he did it would be like df dx. So instead of talking about y and x, it's a function versus x. And then there's also this d dx of f of x. Okay, so you got your Newton ones here, and then your Leibniz, all of these types of things. But every single one of these is really just the derivative of a function. Okay? And your textbook, throughout this chapter, is just going to chuck these at you in random spots. Okay? Find f prime of x. Find dy dx. Find df dx. Find d dx. Find f prime. It's all the same thing. Find the derivative is what they're asking you to do. Okay? So, yeah, Newton stuff, Leibniz stuff, but all the same. All the same. So, okay.